Welcome back, everyone. In this video, I'll be continuing the section on cylindrical shells. Number 2 here, it says find the volume of the solid obtained by rotating the region bounded by y equals x squared and y equals x about the line x equals 2. Now, this is definitely one when you see the picture that maybe you would think about, do I have to use cylindrical shells? Can I use it the other way? So we'll talk about why I would use cylindrical shells just from looking at this. But the first thing I want to do is just visualize it. Now we have probably dealt with using this region specifically before. So y equals x squared is one of them, and y equals x. And we want the region bounded by those two. And the only part that's bounded by those two is this little section right here. Now, regardless if we're going to use x or y, we can see that the bounds are both 0 and 1. But let's go ahead and I'll sketch the region out in our area. Let's go ahead and do that. And we've got our x-axis and our y-axis here. And then let's go ahead and just use different colors here. Let's say y equals x is going to be in this, that's not very straight, in this little red line, y equals x. And then the part of our parabola we'll make in blue, y equals x squared, which was below it. Okay, so we know that the x and y bounds are both 0 and 1, which is fine. And then we want to rotate it about the line x equals 2. So that's the vertical line that hits the x-axis at 2. Well, this is x equals 1, so 2 is going to have some space in between it. Go ahead and use a different color there, 2. And this is our line of revolution. All right, so the question is, why is this in the section of cylindrical shells? Why would we want to use this? Well, the main thing is that when you view rotating around a vertical line, you have two options. If you want to do cylindrical shells, the shells are going to be parallel. So if we wanted to do cylindrical shells, we would look at something like this. And the reason why this is so good is you can tell by the height right away is just the top minus the bottom, x minus x squared. Right? And we can also get the radius of the shell pretty easily. And that's because if we just take a number x here, whatever that happens to be, then the radius, which is the distance directly from the x to the line of revolution, well, this is x minus 2. Technically, we should probably do 2 minus x because we want it to be positive. So r equals 2 minus x, right minus left, bigger minus smaller. We do have to be careful about the radius in this section because the formula for the volumes of revolution by cylindrical shells, there's not an r squared, it's just an r. So when you integrate, if you do this backwards, if you do smaller minus bigger, then you get the negative of all the volume. And really we would want positive volume anyway, because this isn't just an integral, it's representing volume. All right, so that seems like it would work pretty well. We already have the height and the radius pointed out for us. Why would we not want to use the other method? Well, the other method using slicing, whether this is disc or a washer, it's not that you can't do it. One thing though is that you would need the washer method. And whenever we pick a little section out to do the washer or disc method, what we have to make sure we're doing is looking at what the bounds are. And it's always going to be perpendicular to the axis of rotation. So they look something like this. I'll write if we do the disc or washer method, this one specifically is a washer method, it would look like this. So we would be looking at the y bounds. Everything in the integral would have to be in terms of y. So everything inside integral, we can't have x's, we would need y's. Well, the problem is here, it's not impossible to do for this problem. It's not too hard at all. But you'd have to take these equations, see how the ones that's closer to the line of revolution is y equals x squared. We'd have to solve this for x, and it would just be x equals the square root of y, which isn't too bad. But then you have to go through and actually do it. You have to set up, what is your inner and outer radius as well. So really, one of the main reasons I look at this one and see I need cylindrical shells, or I should try cylindrical shells, is the equations along with how I'm rotating it. And that's because when we draw a cylindrical shell out here, we get a vertical slab because it's parallel. And we can easily figure out the height because it's just in terms of our equations already. Now, if we had x equals the square root of y and x equals y, which would be the same thing, but we rotate around this, then I would probably just go ahead and use the washer or disk method because it would be x equals for our equations. So this is telling me I definitely want to use shells. Once again, you can use disk or washer if you prefer because it's possible here, but I'm going to use shells. In the volume here, our bounds on x are from 0 to 1. So that's going to be the bounds on our integral. We have 2 pi in front. We have r, the radius, which is 2 minus x. And we have the height function, x minus x squared dx. Now you can imagine if we had to do the washer method, or we did do the washer method, we would have to do the outer radius squared minus the inner radius squared. We'd have a pi in front. We might have to FOIL all that stuff out. So there's a lot less algebra here because we only have one thing to multiply out, which is this. So let's go ahead and do it. Distribute these to each other. We get 2x minus 2x squared. Distribute the 2. Then distribute the minus x. We get minus x squared plus x cubed dx. And we do have some like terms. Let's go ahead and combine them. We've got 2 pi, the integral from 0 to 1, 2x minus 3x squared plus x cubed dx. And we'll just go ahead and finish this off now. We have the 2 pi in front. We want to integrate 2x. Well, that's 2x squared over 2, which is x squared, minus 3x cubed over 3, because we wouldn't divide by the 3 and those cancel. So you just get minus x cubed, and then we get plus x to the 4th over 4. Nothing to cancel out there. Plug in from 0 to 1. We didn't do any substitutions, so we don't have to worry about the bounds. And we have 2 pi. Plug in x equals 0, or sorry, x equals 1 first, minus x equals 0. When we plug in 1, we get 1 squared, which is 1, minus 1 cubed, which is another 1, plus 1 to the 4th, which is 1 over 4, minus x equals 0. Well, when you plug in x equals 0 here, you get 0, so that's simple enough. And the 1's cancel out here, the 1 and the minus 1, and we have 2 pi. The only thing inside here is 1/4, so 2 pi times 1/4, which equals pi over 2. So the volume of this shape by cylindrical shells is pi over 2. Once again, if you do the washer or disk method, you should also get pi over 2. Nothing special about the method we're using here, just that, in my opinion, cylindrical shells is easier in this situation. But not all situations, of course. There may be a good property to mention now as far as, when can you use both? One might be easier than the other, but when can you use either one? It's really when this section you have drawn out here, the region you're looking at, both functions are one-to-one, meaning they both pass the horizontal line test. They have to be functions, so they automatically pass the vertical line test. So typically, if the region you are rotating is bounded by one-to-one functions, then either the disk or washer method will work. Sorry, disk washer or cylindrical shells will work. Okay, so this one, y equals x, and y equals x squared in general is not one-to-one because it's a parabola, but just from this section, it doesn't failed a horizontal line test. So you could use both. And that's a good indication. Just if you're looking at a general problem, you don't know which one to do. Maybe you're not just working in this section, you're working on some type of assignment that has accumulation of section problems, then this is what you're really looking for. If it's not one-to-one, then we'll have to be careful. We talked about really a good example at the beginning of this section, why you need cylindrical shells. And you could also come up with other ones where when you draw the picture for the left and right or top and bottom, whichever one you're doing, why you would need the disc or washer instead of cylindrical shells. We saw that in the last section. All right, so number 3 here, it says use cylindrical shells to find the volume of the solid obtained by rotating the region bounded by the curve y equals the square root of x, y equals 0, x equals 0, and x equals 1 about the x-axis. Right, so this one you can kind of see that it says about the x-axis. So that might indicate, based on our equations, how we're going to approach this. But let's go ahead and draw the picture. Now keep in mind that it does say use cylindrical shells. They're probably telling us that because it can be done either way, and we just need to get that extra practice with cylindrical shells. Now this is something that's not bad to draw because we only have one equation that's not a horizontal or vertical line, and that's y equals the square root of x. And the y equals the square root of x is just sort of that sideways looking parabola in quadrant 1. We only care to go from x equals 0 to x equals 1, so I'm just going to stop it there. Say this is x equals 0 and this is x equals 1. Now at x equals 1, the y value is also 1, so I'll just go ahead and point out there that that is the point 1 comma 1. And down here is 0 comma 0 where it starts. And I'm just going to draw on the rest of the region. So we got the y equals 0, which is the x-axis. It's automatically stopped at x equals 0, so we don't have to really draw that in. And we do need to draw in the x equals 1, which is the vertical line here at x equals 1. So if you go ahead and graph all 4 of these things, you'll get this little region that we want to rotate. And we want to rotate it about the x-axis. That's our line of revolution or rotation. All right, so we've got our picture drawn and we need to use cylindrical shells. That's the most important thing, is the direction tells us use cylindrical shells. Well, cylindrical shells are always parallel when you draw a little cross section because that's the height of your cylinder. So this is the cylindrical shell. And the thing is, what is the height and the radius? Well, the height, since it's going from left to right, it's the bigger minus the smaller is the right minus the left. Height is x equals 1 minus, well, this is y equals the square root of x. But what's wrong with this is that because our shells are horizontal here, our bounds should be in terms of y. So everything needs to be in terms of y. Right, but that's not hard to do. It's just a little hiccup here, pretty much like a force example from the previous one. The previous one, we didn't have to do any rearrangement, but I talked about it. We need to make this, x equals stuff with y. Right, so we need to make that equation that we're given. It's y equals, we don't want to put square root of x in there. The problem with that is we put the square root of x, then the rest of our integral is going to have y's in it, and this is going to have x, and that's no good. So we need x equals stuff with y. All right, but this is a pretty straightforward equation to solve. Let's go ahead and just do it real quickly. We have y equals the square root of x, and then you just square each side, and you get y squared equals x. So that means in place of x, the height, you get y squared. Right, so we've got the height, and then the radius. What is the radius? Well, you can go ahead and judge based on the picture here. Always important to draw the picture. The radius r, bigger minus the smaller, keep that in mind. R equals, and what is r here? Well, don't get confused and look at the curve here. It's not r equals the curve. The thing you want to remember why we are not going to be using the radius as the equation of the curve here is we're just running through the y values. That's what the radius does, is it runs through the y values 0 to 1. Sort of like when we did the opposite picture up here. For the radius here, we didn't use left minus right to represent the radius because the radius itself is how far we are extending away from the vertical line of x equals 2 last time. So remember that it does go out, until we actually hit, but visibly all we're doing is running through the possible y values here. So the radius is just the big minus the small here. The big is just the y value minus the small value of y, which equals 0. So the radius is just y. Right? And once again, it's just running through the y values. So I think for cylindrical shells, at least the ones that are like this, where you have horizontal cylindrical shells, it just looks a little more confusing, at least to me. And you just have to be careful and realize that the height uses the curves here. So x equals 1, x equals y squared, the green one. And then the radius is just running through the possible y values. And we're going up from the y value of 0 to the y value of 1. Right? But we do have everything we need to set up and actually integrate now, because we have the height, we have the radius, and we also know we're going from y equals 0 to y equals 1. So the volume V here would be the 2 pi out front, integrate 0 to 1, and the radius formula is r, and the height formula is y, and the height formula is 1 minus y squared dy. So like always, just simplify these things and then you can proceed to integrate. So we can distribute the y through and we get y minus y cubed dy. And now we can integrate each part. So the 2 pi's out front. Integral of y is y squared over 2 minus the integral of y cubed is y to the 4th over 4. Plugging in from 0 to 1. And let's go ahead and do it down here, make some room. And we got the 2 pi out front. We've got y equals 0, or y equals 1. Don't know why I keep saying the bottom one first, minus, and then y equals 0. When we plug in y equals 1, we get 1 squared, which is 1 over 2, minus 1 to the 4th, which is 1 over 4. Then minus y equals 0. Another one that does give us 0 when we plug it in. And we'll go ahead and simplify this. And we'll go ahead and look at this. This is 0, so that's not helpful. Not going to change anything. For the 1 in here, we have 1/2 minus 1/4. If it helps, multiply the 1/2 by 2 over 2, so you can get a common denominator. This is 2 over 4 minus 1 over 4, which simplifies to 1 over 4. So we got 2 pi times 1 over 4, which is pi over 2. Oddly enough, it is the same volume as the previous problem, but it is, a different shape. It just happens to have the same volume. One thing I encourage you, if you're not comfortable with the cylindrical shells, especially with this problem, is it shouldn't be hard to do this problem with the disc. So you would run through the vertical slabs here, looking at the radius of your disc as you rotate them. And this would be the disc method if you use the disc or washer method, because the entire line of revolution here is touching the entire region. So we'd have that. It shouldn't be hard to set up and integrate and solve that, and you should get the same thing. And it might give you the confidence that you are doing things correctly. Just a note though that you can't do both methods with every problem, so you do have to get comfortable with cylindrical shells. All right, now that's mostly what this section is about. In the next section, I'm just going to go through a few problems where I talk about the differences. How would you know to use cylindrical shells versus the washer or disc method? I've pretty much talked about them as I've gone through these problems in this section. So if you're comfortable with that, you can kind of think about it as an optional video, but I wanted to make sure to throw it in so we could talk about some examples specifically. So I'll see you there.